Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ali Fatimi bin Nizam, and my teammate and I will present about Chapter 5 Hydrocarbon. For question A, I will present the structure of J, K, and L. J is 2-methylpropane. J is an alkane as it can react with bromine and dichlorometane in dark. And J will have branch, which means alkyl group, that make the structure become shorter and thicker. It also makes the 2-methylpropane has the lowest boiling point. For K, K is 1-butane. In 1-butane structure, it only has one alkyl group that is present on one side. Hence, it has a weaker dipole moment, making it less ionic. So, it has a lower boiling point. K also is alkane because it can react with bromine and dichlorometane in dark. For L, L is 2-butane. In 2-butane structure, both alkyl groups are present on the same side. Hence, it has a higher dipole moment, making it more ionic. So, it has a higher boiling point. L also is alkane because it can react with bromine and dichlorometane in dark.
The next hydrocarbon with molecular formula C4H8 is M, cyclobutane. Cyclobutane is a cycloalkane. Cycloalkane is a saturated hydrocarbon as it did not react with bromine in dichlorometane, CH2Cl2. It is not as reactive as other hydrocarbon. This is because cycloalkane does not possess double or triple bond that can undergo addition reaction. The next one is N, methylcyclopropane. The explanation for N is the same as M, as both M and N are cycloalkane. Why J has the lowest bonding point? J has the lowest bonding point compared to K and L because of the molecular shape of J that is shorter and fatter in shape with branch compared to K and L due to presence of branching of methyl. The boiling point of J is also the lowest because it has lower contact surface area compared to K and L, hence weaker van der Waals forces of attraction that require smaller amount of energy to break the bond between the molecules. The diagram below shows the molecular shape of J with branching of methyl. Branches will reduce the boiling point because molecules with higher number of branches will have less contact surface area. The lesser the number of branches, the lesser London dispersion forces between the non-polar molecule.
Alright, so for part C, we are asked to give two isomers of C4H8 that react with HBr to give optically active product. So the first isomer of C4H8 that react with HBr to give optically active product is K, which is 1-butane. So the equation is as follows. 1-butane will react with HBr to give two products, which is the major product is 2-bromobutane and the minor product is 1-bromobutane. So the second isomer of C4H8 that react with HBr to give optically active product is L, which is 2-butane. So the equation for 2-butane is as follows. 2-butane will react with HBr to give one only product, which is 2-bromobutane. So this 2-bromobutane is actually the optically active product obtained from this reaction. 2-bromobutane is said to be optically active product because it has chirality center, which is a carbon atom in the molecule that is bonded to 4 different groups of atom. In this case, this carbon atom is bonded to methyl group, ethyl group, hydrogen atom, and bromine atom. So this gives 2-bromobutane its property to be optically active, which is it has ability to rotate plane polarized light to the left and to the right. Alright, so this hydrohalogenation reaction actually follows electrophilic addition mechanism. This mechanism involves two steps. The first step is the addition of an electrophile. Alright, so the hydrogen bromide molecule HBr is a polar molecule because the bromine is more electronegative than the hydrogen atom. So the bromine atom will attract all the electrons toward itself, leaving the hydrogen atom to be partially positive, delta plus, and the bromine atom to be partially negative, delta minus. So what will happen here in this mechanism is the pi electron in the carbon-carbon double bond into butane will attack the electrophile, the H+, and the H+ will attach to one of the carbon in the carbon-carbon double bond. So the rule to determine the position of the attachment of the electrophile, or in this case the H+, actually follows Markovnikov Rule. Markovnikov Rule states that the electrophile, the H+, will attach to the carbon that is bonded to the greatest number of hydrogen atom. So when the electrophile bonded to one of the carbon in the carbon-carbon double bond, this will leave the other carbon to be positively charged, and this will form a carbocation ion. And in this mechanism, we will also produce a nucleophile, or in this case, the bromide ion. So moving on to the second step, which is the formation of product from the carbocation ion. So what will happen here is the nucleophile, or the bromide ion, Br-, will attack the positively charged carbon, or the carbocation ion, and it will attach itself to the carbon, and it will produce a product which is 2-bromobutane, and 2-bromobutane is the optically active product.
Alright, let's move to the D section of the question, which is the one chemical test to distinguish between J and M. So what is the chemical test that we use? The chemical test that we use is the Bayes test, and the reagent used is the cold dilute and basic potassium permanganate, which is the KMnO4. So the hydrocarbon itself that we use for the first one is the J, 2-methylpropane. So we can see here from the equation, the KMnO4 is originally purple in color, but after we do this test, we will get the two product, which is 2-methylpropane 1,3-diol, and also we will get the MnO2, which is brown precipitate formed. So the observation that we should get is the purple solution will be decolorized and brown precipitate should be formed. Alright, let's move to the next hydrocarbon, which is M, which is in this case is the cyclobutane. So if we do the Bayes test on cyclobutane, we will see that no reaction occurred. Why does this happen? This is because cyclobutane is alkane is saturated hydrocarbons, which means they will be bonded to as many hydrogen atoms as possible. So potassium permanganate will not react to them as they are saturated. So from this test, we should get observation no observable change at all. Alright, let's move on to the E section of the questions, which is structures of the isomers of C4H8, which shows geometrical isomerism. So if we come across of this type of question, what should we do first? The first thing that we should do is know what is geometrical isomerism. So geometrical isomerism is geometric isomers, which also known as the cis-trans isomers, are the stereoisomers that are differ by a group being on the same side, which is called as the cis isomer, or groups that are being on the opposite side, which is called as the trans isomer, of a site of rigidity in a molecule. So let's see. So the first one, we have the cis-2-butene. As we can see, the CH3 are being on the same side, on the what we call the lower side of the molecule itself. So while the trans-2-butene, we have the CH3 on the opposite side of the molecule itself. You see, one being on the top and one being on the bottom.
For Quranic verbs, the functional group presented is hydrocarbon. The plant chosen is olive, and related Quranic verse is from Surah Al-An'am, ayah 141. A'udzu billahi minasy syaithanir rajim. Bismillahirrahmanirrahim. Wa huwa allazi ansha'a jannatin ma'rushatin wa ghayra ma'rushat. والنخل والزرع مختلفا أكله والزيتون والرمان متشابها وغير متشابه كلوا من ثمره إذا أثمر وآتوا حقه يوم حصاده ولا تسرفوا إنه لا يحب المسرفين. And he is who caused garden to grow, both sterilized and unsterilized, and palms, tree and crops of different kinds of food, and olive and pomegranates, similar and dissimilar, eat of each of its group fruit when it is, and give its due on the day of its harvest, and do not be excessive. Indeed, it does not like those who commit excess. One of the components in olive is 6,10-dimethyl 1-androgen is one of the hydrocarbon component in olive oil that occur naturally in the olive plant and can be harvested by processing the olive to produce a refined olive oil. The 6,10-dimethyl 1-androgen contains the alkane functional group. The structure is shown. Composition of the plant. 10 grams of the red olive provide about 116 calories, 10.9 grams fat, 0.84 grams protein, 6.04 grams carbohydrate, 1.6 gram fiber, 88 mg calcium, and 0.9 mg of vitamin C. The benefit of the olive. Olive are rich of antioxidant properties that have been proven to reduce the risk of the chronic illness such as heart disease and cancer. It also helps to significantly decrease blood level of the glutathione that is one of the most powerful antioxidants in the body. Olive also rich in oleic acid that can help to regulate cholesterol level and protect LDL cholesterol from oxidation. The high antioxidant and oleic acid contents in olive can also disrupt the life cycle of the cancer in the breast, colon, and stomach, thus help to reduce the risk of cancer in the body. This is reference that we use to make this assignment. That's all from us. Thank you for listening.